We are going to continue with the power series, and in those yellow boxes, we just have a couple more properties: our continuity property, our differentiation property, and our integration property. Those last two, the differentiation, yes, and integration property are the next two examples. Believe it or not, we can find derivatives of series. It looks kind of crazy, but we can. So example 8, we're going to use the differentiation property on the power series f of x equals 1 over 1 minus x. We know that that's really x to the k power, or x to the n power. We want to find a power series that represents f prime of x being equal to 1 over 1 minus x squared. So let's look at all of these things. I'm going to start by writing the equal pieces next to each other. So I know that f of x is the same thing as 1 over 1 minus x, which is the same thing as the series from 0 to infinity of x to the k. So we know that all three of those things are the same if we go to graph them. Now I want to find the derivative. So I'm going to start with my notation, f prime of x. We know that means first derivative. On this term on the inside, we could do this as a quotient rule. We could also bring this to the top. 1 over 1 minus x is the same thing as 1 minus x to the negative 1. So this would really be negative 1 minus x to the negative 2 times the negative 1. So 1 over 1 minus x squared. Which is exactly what's given in the problem. So what does that look like as a series? So you can find the derivative. There's my series symbol from 0 to infinity, bring k to the front, x to the k minus 1. A power rule, just like we've always had. Now, if I look at the expanded form, believe it or not, it works for that as well. If I had 1 plus x squared, you can take the derivative of each term. We've got 0 plus 1 plus 2x, and it works. Isn't that kind of crazy? Kind of crazy. So, differentiation property. Now we want to find the power series that's represented by natural log of 1 over 1 minus x. So what's going on here? So these problems are kind of like proofs. If I have the natural log of 1 over 1 minus x, I know that's not anything directly with the power series. So what I'm going to do is find the derivative of this. So f of x is equal to natural log of 1 over 1 minus x. F prime of x is going to be 1 over 1 minus x, 1 over u, times du dx. And that derivative we just actually found in the last example as well. So negative 1 minus x to the negative 2 times negative 1. So if I look at this or put this together, I've got positive 1 minus x squared in the denominator, and I have a 1 minus x in the numerator. This is all still the first derivative. And this simplifies. I've got 1 over 1 minus x. My husband's out here spraying bug spray. So I want to know natural log of x. So the question is, how do I get from this expression back to natural log of x? And the answer is I find the antiderivative. I look for edit that part out. I look for the antiderivative, so I integrate. So if I integrate 1 over 1 minus x and I integrate f prime of x, right? Then I'm back at f of x is equal to natural log of 1 minus x. 1 minus x. And there's a negative in the front because I have to divide by negative 1. So if there's a negative in the front, that's really 1 over, because it's a negative 1 exponent, 1 over 1 minus x. Now, I've totally neglected that series piece. So I want to come back up here to what's in purple. We know that 1 over x is the same thing as the power series. So from k equals 0 to infinity, x to the k. So if I want to integrate This piece and this piece, I can also integrate the series. It looks weird, it feels weird, but it works. So if I integrate this, I now have the series k equals 0 to infinity, x to the k plus 1 over k plus 1. You add 1 to the exponent and divide, just like you do with regular antiderivatives. Pardon my handwriting here. So all together, this should be equal. I know that the series k equals 0 to infinity, x to the k plus 1 over k plus 1 is the same thing as natural log of 1 over 1 minus x. That's on the absolute value, which is the same thing as the original function. Now, I didn't ask for the expanded form here, but it would still work the same way, that my series is equal to the function, which is equal to the expanded form of 1 plus x squared plus x cubed, dot, dot, dot. And you can integrate that as well. So this becomes x plus x squared over 2 plus x to the third over 3 plus x to the fourth over 4. So no matter what form you're in, whether it's the function, the series, or the expanded form, you can integrate those as well. Just want to make sure I don't miss anything. All right, we want to find the interval of convergence for this. So we're going to look at the endpoints. Now, the radius of convergence is 1. Radius of convergence is equal to 1. So if we're centered at 0, I know that my two endpoints are 1 and -1. So we want to check out those endpoints. So what are we going to do with 1 and -1? We're going to put them into the original series. Well, we're going to put it into the one that we calculated, the one that we found. So this is k equals 0 to infinity, 1 to the k plus 1 over k plus 1. 1 is always 1, so this is 1 over k plus 1. Here's my sigma. Does this one converge or diverge? This diverges. It's harmonic. It would also diverge by the integral test. We talked about those. So let's try -1. So now I have -1 to the k plus 1 over k plus 1. So this is -1 to the k, -1 to the first over k plus 1. Because of this piece, it now alternates. So because it alternates, this one converges by the alternating series test, and that would be conditionally convergent. So I know that we're out of space here, but your interval of convergence would be -1, which is less than x, which is less than 1, and it converges at -1, so that's underlined. So this is your interval of convergence. Okay. And then there was a part C, which was to find the natural log of 2. To find the natural log of 2, when does that really happen? We're definitely out of space here. So this is part C, we'll write in red. We want to find the natural log of 2, but we were given this expression, natural log of 1 over 1 minus x. So what would x have to be equal to in order to make this be the natural log of 2? Well, we can't substitute directly, but what happens if I have the natural log of 1 over 1 minus a -1? This becomes natural log of 1/2. And if you remember natural log rules, this is natural log of 1 minus natural log of 2. Natural log of 1 is 0, so this is negative natural log of 2. So we can get close. So what we would do in our power series is we would let x equal -1. And then we would substitute that into all the power series. This doesn't make sense to you. I'm okay with that. I'm definitely okay with that. But it works out to be the sum k equals 0 to infinity, -1 to the k over k plus 1. That was a terrible explanation, but if you want to look at that, it's in your book on page 785. And then finally, we're actually going to skip this one. Show that the power series representation for the inverse of tangent is the following, then find the radius of convergence and the integral of convergence. It's a proof problem. They want you to prove the inverse tangent equals that expanded form and also that series form. It's honestly not necessary. If you wanted to, again, it's on page 785. They use the fact that the derivative of inverse tangent is 1 over 1 plus x squared. And find the derivative of all of those other things. And then you can substitute -x squared into the power series and integrate it to get back to all of this. I'm not so worried about that. It's going to be on that red paper that you have, that formula sheet. If you have it memorized, great. And if you don't, just use it for a reference when we get to our test. I fully realize you might not be able to memorize all these. So good luck with 10-8. That's all of it finally.